Hello students, in this session on matrix space we are going to study concept of interior points of a subset of matrix space. So we are familiar that if you take say some circle, we know that what are the interior points of circle. So except boundary, these are interior points. For triangle, these are interior point, interior path, exterior path, right? And this is boundary path, boundary of that region. Similarly, for any shape in R2, you are familiar with what will be the interior part of that region, what is exterior part, and what are the points lying on boundary of that set, etc. So we are using interior, exterior, boundary concepts. So here we are going to talk about interior points of matrix space. For intervals also, if I take some interval AB, then what is the point lying inside that interval, which are the end points of that interval, which points doesn't lie in that interval. Depending on this, we are going to talk about the concept of interior point. So mathematical definition of interior point. Okay. So definition, let XD be a matrix space, be a matrix space, whatever your matrix space may be, and A be subset of X. Then A belongs to A is interior point of A is interior point of A if A is neighborhood of A. A is neighborhood of A. That is, if there exists some radius greater than 0 such that open sphere about A is contained in A. From this, A interior set is equal to set of A belongs to A such that SRA is contained in A for some R greater than 0. Is set of all interior points of A. So this is the notation for interior point set. Interior point set. Now if I take A to be open set, then for that open set, if A is open, then for any A belongs to A, there exists R greater than 0 such that SRA is contained in A. Okay. So note, if A is open subset of matrix space XD, then A interior must be equal to A. A interior is equal to A. Every point of A becomes interior point of A. Okay. By definition of interior point. Okay. By definition of interior point and open set. Right. Now we'll take some examples. In RU, if I take first I is equal to say open interval AB, close interval AB, or open close interval AB, or close open interval AB. Then I interior must be equal to open interval AB. I interior must be equal to AB. For closedness, if I take this closed interval AB, for this if I take any x here or here, so here SRX is contained in AB, SRX is contained in AB for every for R is equal to minimum of, if I take minimum of mod of A minus X or mod of B minus X by 2 greater than 0. Okay. And X belongs to open interval AB. Now for A SRA, this become A minus R to A plus R. This is not subset of AB. Similarly, SRB is equal to B minus R to B plus R. This is not subset of AB. Whatever other point X in AB may be, that SRX is the subset of closed interval AB because R equal to minimum of mod A minus X and mod B minus X greater than 0 work. Okay. If I take open interval here or for this here, this works there, but for endpoints, these open spheres are not subsets of these, and that's why I interior is equal to open interval AB. Secondly, if I take example, say A is equal to any non-empty finite set, non-empty finite set in R, or if I take N, W or Q or Q complement is equal to P, this sets, Cantor set. Now here you can observe finite set in R. If I take for any A belongs to A, for A belongs to A, what is the SRA? Is A minus R to A plus R. Is interval, open interval, not subset of A, because every finite set can't contain interval. Set of natural numbers, set of whole numbers, set of rational numbers, set of irrationals, set of Cantor set doesn't contain any interval. Doesn't contain any interval. And if I take the open sphere about any point, it is always interval, non-empty interval. So that intervals must not be subsets of these sets. Must not be subsets of these sets. Okay. These sets. If A is equal to this are subsets of R, then A interior is equal to phi. A interior must be equal to phi. Every point is not interior point of those sets. Interior point of those sets. In R2 now, with respect to usual metric, in R2, if I take some line with respect to usual metric, if I take any point here and if I take the neighborhood about that, even though it is too small, that contains points outside of that line. So line is not open, line is not, its interior will become empty set. Every point on line must not be interior point. Similarly, if I take some boundary set, then it must not be like circle. If I take some circle, If I take any point on this and open sphere about that in R2 with respect to usual metric D2 or your D infinity or D1, in that case, any point on those lines or circles or triangle or parallelogram must not be interior points. But if I take this just region, interior point of this, then I can find open spheres very small. I can find the distance between that point and boundary of that region. Then that open sphere is subset of that, and every point becomes interior point of that. The point becomes interior point of that. So this is the geometrical concept of interior point. Okay. Our aim is to do some results now. That results will be helpful to find interiors of the set. So take the theorem. Let XD be a metric space, XD be a metric space, and A be subset of X. Then 1. A interior is open set in X. A interior is open set in X. Second, A interior is largest open subset of X containing A. Is largest open subset of X containing A. Third one, A is open if and only if A interior is equal to A. A is open if and only if A interior is equal to A. And fourth, A interior is union of all open subsets of X contained in A. A interior is union of all open subsets of X contained in A. Contained in A. So we'll prove one by one. So by definition, what is A interior? A interior is set of A belongs to A such that SRA is contained in A for some R greater than 0. So first to show A interior is open set. So let A belongs to A interior. A interior. Then to show there exists R greater than 0 such that open sphere about A is subset of A interior. Yes, R A is contained in A interior. Okay. So clearly SRA is subset of A, but I have to show that SRA is subset of A interior. SRA is subset of A interior. Okay. So let clearly SRA is subset of A. So by definition of A interior, for A belongs to A, there exists R greater than 0 such that SRA is subset of A. Okay. To show SRA is contained in SRA is contained in A interior. So let B belongs to SRA. Now since SRA is a open sphere and hence open set, hence open set. Therefore, for B belongs to SRA, there exists some radius R1 greater than 0 such that SR1B is contained in SRA. Is contained in SRA. This implies SR1B is contained in SR1B is contained in A. This implies B is interior point of A. Interior point of A, right? Therefore, B belongs to A interior for every B belongs to SRA as B is arbitrary. B is arbitrary. What this implies? This implies SRA must be subset of A interior. SRA must be subset of A interior. Okay. Thus, A interior is open. Thus, for any A belongs to A interior, there exists R greater than 0 such that SRA is contained in A interior. And therefore, A interior is open set in X. Now our aim is to show that A interior is the largest open subset contained in A. What is our second aim? To show A interior is largest open subset of X contained in A. Contained in A. So for this, suppose there is other set. For this, suppose G is open subset of X such that A interior is contained in G is contained in A. Then for G belongs to G, there exists R greater than 0 such that open sphere about G is contained in as G is open, is contained in A. That is SRG is contained in A for every G belongs to G. Okay. And therefore, G is interior point of A, or G belongs to A interior for every G belongs to G. This implies G is subset of A interior. Okay. So from this part, say this is 1, this is 2. From 1 and 2, A interior must be equal to G. So whenever I assume that there is some open subset which is a superset of A interior and subset of A, then that two sets must coincide. Okay. So from this, A interior is largest open subset of X contained in A. Our third aim is to show that A is open if and only if A interior is equal to A. Third, to show A is open if and only if A interior is equal to A. So, for any subset A, for A subset of X, A interior is subset of A by definition. By definition. Now, if A is open, then for any A belongs to A, there exists R greater than 0 such that SRA is contained in A. Implies A belongs to A interior for every A belongs to A. For every A belongs to A. And therefore, A is subset of A interior. So this is 1 and this is 2. From 1 and 2, A is equal to A interior if A is open. A is open. Now, conversely, if A interior is equal to A, then by 1 A interior is open set. Then by 1 A interior is open set. In X implies A is open in X. A is open in X. Now we have to show that A interior is union of all open subsets of X contained in A. Contained in A. A interior is also one largest open subset of X contained in A. Contained in A. Therefore, union of all open subsets of X contained in A must be equal to A interior. Okay. 4. To show A interior is union of all open sets in X contained in A. So by 2, A interior is largest open set in X contained in A, and therefore result hold. If I take any other open set contained in A, then it must be subset of A interior. It must be subset of A interior because, okay, as any other open set contained in A lies in A interior. And therefore result hold. So with the discussion, we'll stop the first session on interior points here. So thank you for listening my session. Bye bye.